we're going to get started. So, first thing, I'd like you to graph the spiral of Archimedes. So that is, so what you're going to have to do is, because you're going to be with T's today, you know, when we're graphing in parametric mode, we graph with T's. So this is going to be T cosine of T, T sine of T, and 0 to 4 pi. The other kicker is, up in the corner, we need to be in radians, because we're dealing with radians here, okay? Because we're going from 0 to 4 pi, that says that we need to be, so you need to take your cursor up into that upper corner and click on the DEG, put it in RAD, okay? So graph that one on this window setting. Okay, so you'll have to adjust, so you got, not only you got to put that in, you also got to adjust the window. It's great. Do you know how to use your calculator? So it should look like that. Or it should just be a spiral that goes around twice. Okay. Questions, comments, concerns, clarifications? Kicker that you're probably finding is you needed to put the multiplication sign because you got a variable in front. You need to put that multiplication sign in front of your trig functions. Okay? All right. Good times. All righty. So we're going to be talking motion in the plane. Okay? Meaning, we're going to have objects that are going to be thrown vertically. We're going to have objects that are going to be thrown at an angle. Okay? We're going to have all of those different things. Okay? So, it can be shown using calculus that any object that is thrown or launched, we might even say launched if we have something like that, vertically into the air, from an initial height of h sub 0, okay, so that's our initial height, with an initial velocity. Now, do those two things matter in terms of the path, the height of the object? How high I launch it from and how quickly I launch it from. Does that have anything to do with the height function, if you will? Lots to do with it, right? Okay, the higher we launch the object from, the higher the object's going to be, right? The bigger the height. Okay, the more force we launch it with, the farther up it's going to go. Okay, so right now we are literally just talking straight up and straight down. Okay, that's all we're talking about right now: straight up and straight down. Okay. So how quickly or how much force I use to launch it with, make sure I'm not underneath the light, okay? If I launch it with more force, I hit the ceiling. If I launch it with less force, it barely goes up and I barely catch it. Okay? Okay? So those two both play effect. So it shows us that we have this formula then. H of t, so the height of our object after t seconds is negative 16 t squared plus v sub 0, that's our initial velocity, times t, plus h sub 0. Okay? So that's our initial velocity, and our height have a definite effect on that. Okay? So if you were to graph this one, it would have a graph of time versus height. What would the graph of time versus height look like? Upside down parabola. Okay? So the time versus height graph would look like this, even though the actual flight of that same object would look like this, straight up and straight down. Okay? So the actual would look like that, where it would go straight up and straight down. Okay? If we're standing on the side of a building or on a cliff or something like that. Okay? All right? So, from the top of a 30-foot building, a ball is thrown vertically upward with an initial velocity of 50 feet per second. What does the ball do? So in terms of function mode, where again we are height versus time, what would our function be? H of t would equal what? What are they all going to start with? Negative 16t squared plus what? 50t, right? Because my initial velocity was 50 plus what? Plus 30, because my initial height was 30. Okay. So if I were to graph that, we would have a initial height here, or a y-intercept of 0, 30, right? And then our object would go up. And come back down, and it would hit the ground at a certain point. Yes? Okay. Well, let's model that on our calculators. So the first thing we're going to do is we're going to have to go back into function mode. So graph entry edit. We're going to switch it back to function mode. Okay? I think, yeah, no, we're going to be way out of the circle of Archimedes, so I don't have to worry about that one. Then we type in negative 16. Now instead of t, though, x, because I'm a function of x. So negative 16x squared plus 50x plus 30. And when I graph that, okay, so let me get rid of my, that one so that we can see it. There we go. Now we can see it. Looks like we got to go up a little higher, right? Started at 30. We're only going up to 15. So in terms of x's, only really got to go out to 5. I'm just literally checking to see if, oh, we went way too high. Okay, so 10, 20, 30, 40, 50, 60, 70. We could go to 100. Okay, so your window should look like this. Now, we can use that to find some pretty important things. Okay? Upside down parabola has a vertex that is also the, in this situation, it would be the what would the vertex of this parabola be? So be the maximum height. Okay, so we can find the maximum height of our ball. We can do that very quickly by analyzing our graph for the maximum. What does that maximum point tell us? How high does our ball get? (69.063 feet. When does it reach that height? At 1.56 seconds. Okay, so we release it 1.56 seconds. It's a tongue twister. Later, okay, the ball reaches its maximum height, and then it starts to descend. Right? Okay. What else can we find from this graph? To land, what would that one be? The x, so the 0. Okay, so let's analyze this graph for a 0. So how long was this ball in the air? 3.64 seconds. Okay, so we launch it 30 feet in the air, we throw it up, it goes up, it hits its maximum height of 69.06 feet after 1.56 seconds, then it starts to come down, and it lands on the ground after 3.64 seconds. Okay? Okay, so we've got that one. Now, let's parametrically do this exact same thing. What the parametric mode is going to give us is it's going to give us the precise flight of the ball. So like on this last slide, we had here, this was what the height versus time. Then we had the actual flight. The actual flight is going to be the parametric mode for this one. And so for the parametric mode for this one, we are going to, we are going to set some x value. I don't care what that x value is, it just can't be 0. So I'm going to choose 1. Because if it's 0, it's going to be flying on the axes, and we're going to not see it. Okay? So we want to be able to see it. Then, for the y value, now this is going to be our negative 16t squared plus 50t plus 30. Same function. Our t range will go from 0, that's when we initially release the object, but it's got to go past what? What does our t have to go farther than? 3.64. Okay, so we could do 4 there for our t value. If it goes less than 3.64, then our ball is going to suddenly be, it's going to get closer and closer to the ground, and it's going to just stop. It's not going to hit the ground. So we want it to go past there. Okay? So parametrically now, we can graph that same thing. I'm going to start a new graph just because then it's not on the same one. We've got to switch over now to parametrics. 1 there. Negative 16, switching back to t's now. Plus 50t plus 30. we said to 4. There it is. But now we got to adjust our window again. Our window could be the same settings that we had before. -1 to 5 by 1s. -15 to 100 by 10s. Same window. Here now is the ball's flight. Now the downfall with technology is back in the day, now I can say this because this was back in the day, we had TI-82s, okay? They were handheld graphers like you have here, but their processor was slow, okay? And the slow processor allowed you, as soon as you clicked it to graph, it would actually it would like show the object going up because it was thinking about where it needed to calculate it. So it would show the object going up, and then it would show it stop, and then it would show it coming back down. It was actually, that was one of the cool parts. But now with technology, the processor is so fast. Seamus, come on, man. You just get up and move around, okay? All right? But the processors are so fast now that it's just instantaneous. Okay? So they don't, the processors are so much better, we don't get that cool aspect of it anymore. Okay? Cool. So now on this graph, now that I can write on it, we know that this point, this maximum height here, is at the point 1, 69.063 feet, because it's at the same maximum height as the other one. We also know that that's at a t-value of 1.5625 seconds. Okay. We know that this point down here is the point 1, 0, and we know that that is a t-value at 3.6401. We know both of those based off of graphing just the function of the height. Okay? Questions on that? Nico? In terms of the parametric time. Now this one would be height here, but this would be my vertical height here versus my horizontal height here. Or I shouldn't say horizontal height, horizontal distance. This. Looks too much like an 8. Okay. Let me take a peek at the next slide. Okay. So one of the things that we need to, okay, I'll put it here, put it in parametric. I'll go way down to the bottom. Okay. One of the things that you need to be very cognizant of, especially in terms of the two different kinds of graphs, over here, if we're making a chart to figure out points, then this is time versus height, which is t versus your vertical distance, I'll say. In parametric mode, we have a 3-column chart where we've got t is time, x is our horizontal distance, or x of t, you'll have that function defined for you, or you'll have to make that function. And then you'll have the y column will be the vertical distance, which will be y of t, that function. Okay? So now we're standing on top of a building, and instead of launching a ball vertically, now I'm going to launch a ball. I'll go down this way. So actually, hold on, wait right there. And we're going to launch a ball. We're going to launch a ball vertically, and so it's going to go out and down, and then we're going to see when it hits the ground. All that fun stuff. Okay? Yep. So it's coming back. You know what I mean? It comes back just like that. Okay? We're launching it at an angle, so now it's going out. So now we're going to have some horizontal distance to go along with that. Okay? So from the top of a 30-foot building, a ball is thrown at an angle of 65 degrees with an initial velocity of 50 feet per second. We will assume gravity is the only force acting on the ball. How does this affect our parametric equations? Well, before, like 5 minutes ago, our x of t was just some number, right? We just made it some number. In our case, it was 1. And our y of t was negative 16 t squared plus v sub 0 t plus h sub 0. Okay? Now that we're launching at an angle, our x of t is going to be v sub 0 times the cosine of theta times t. So we have that initial velocity, we have that angle involved, and it's going to be times t. Y of t is now going to be negative 16 t squared plus v sub 0 sine of theta times t plus h sub 0. Which I think you have written down there in letter B.
Is the angle going to be in degrees, or is it just going to switch radians?
Angle will typically be in degrees, and I'm going to show you how, if you don't want to keep switching back and forth on your calculator, I'll show you the manual override to it here when we get into it. Okay? Bless you. Okay. Yeah, we'll just do it all in here because we got it all right here. Actually, yeah, we'll go here and we'll do it here. All right. Okay. So our horizontal position function is going to become now x of t is going to be, our initial velocity was 50 cosine of 65 times t. 65 degrees, that is. Okay? Our vertical positioning is going to be y of t is negative 16 t squared plus 50 sine of 65 degrees times t plus 30. Okay? And what the parametric function will do for us now, because remember the parametric function gives us the actual path of the ball or of the object. Okay? So the actual graph that we're going to see now, I'll go back a slide, is going to look like the actual model of the graph or of the actual flight where the ball is going to go up or the object is going to go up and out. Then gravity is going to take a hold and it's going to come down and it's going to come crashing down and hit the ground. Okay? All right? So let's type this in now on our calculadoras. I'm going to use this same exact graph. I'm just going to go and I'm going to change it out. So now my x sub 2, or my x here, is going to be, open parentheses, 50 cosine of 65. Now I'm in radians on my calculator. So the manual override for that is down here in pi, I can put in the degree symbol, and now it doesn't see it as 65 radians. It sees it as 65 degrees. Okay? The other option is, before you start typing this in, because if you do this after you type it in, it will erase it for you, is switching that, drawing your cursor up to the radians and then clicking it to degrees. Okay? Then I've got to double close out, and then I need my t. In terms of this one, I just need an open parentheses there, and then I need a 50 sine of 65, and here again I've got to add in the degree symbol. But then I got to go past t and close off that parenthesis. Now when I hit enter, I'm going to see the flight of my ball, but I'm only going out the first 5 feet, right? This ball is now flying outwards, so I'm going to have to change my window. And now we've got to do some estimating. X's are what's going to change. The maximum of the ball shouldn't really change, okay? Because we went from straight up to now at an angle, so the maximum of the ball will change, but the window shouldn't have to. Roughly, I don't know, I would say let's go out 50. Whoa, tap the brakes. I'm going to go negative 10 here now just because we're going to be out just a little bit. Let's go out 50. Let's go by tens. Didn't go out far enough, right, with 50. So I got to go out even farther. Oops, not tab. Let's go out 150. 150 probably a little too much, right? 10, 20, 30, 40, 50, 60, 70, so we could have gotten by with 100. Okay? With me so far? Now, here's the downfall with parametrics. The downfall of the TI Inspire and the parametrics is that all of your analyzings don't necessarily work. I can't get a maximum of it because it's asking me to choose this particular graph, and it won't let me choose the graph because it just doesn't do it. So what we have to do then is we've got to go back to our function. Okay? And so for me, that was this one. We're going to go back to this one, and we're going to just put in, escape. We're just going back to the function one, and we're going to just give me the y value, because look what we got from the y value before. We got the maximum height, we got the time that it took to go out there, and we got the time that the ball was in the air. Okay? So if I just tweak this maximum height one to what my y value was before, come on, or not, I'll come over here. Times 50 times now all of those have also been tweaked. Okay? So this now tells us that the ball was in the air for a grand total of 3.386 seconds, reached a maximum height of 62.086 feet, and it reached that maximum height at 1.41 seconds. Okay? Now, give me a second here. Okay, so this was the height of the ball. This was how far away the ball landed. This is actual path of the ball. Okay? So this then tells me that it reaches a maximum height of 62.086 feet. This tells me that the ball is in the air for that long. Okay? We will also be asking you questions like, how far away did the ball land? How would you figure out how far away that the ball landed from this? What's up? No? What part of the parametric is the horizontal distance, or how far away the ball landed? X, right? What would I need to plug into X to find how far away the ball landed? Where would I plug it in for? T. I would plug this value here in for T right there, and that would give me the distance away that the ball landed. Okay? We also might ask, how far away the maximum height was. Then we would take this 1.4161 number and plug it in the same spot. That tells me how far out the ball reached its maximum height. Okay? Good times. Okay? Let me introduce you to an old friend of mine named Alfred Delilah. Some of you may know who Alfred Delilah is.
Hi, my name's Alfred Delia.
Can't hear him.
At home they call
Why
me
can't we
Big
hear Big Al?
And I hit dingers.
Oh, I know why. I gotta go to my settings. Hold on, let me pause this video. Now we'll see if it works again.
Delia. At home they call me Big Al, and I hit dingers.
Big Al hits dingers. Alright? Big Al? He's just a kid. Alright? So Big Al hits a ball at an angle of 28 degrees with an initial velocity of 75 feet per second at a height of 3.5 feet. Will he hit a home run if the ball follows the left field line where the Little League fence is 190 feet away and it's 4 feet high? Okay? All right? So we've got two different parametric equations going on here. The first parametric equation we got is Big Al. Okay? So we got to come up with his parametric equation. Okay? All right? So x of t is going to equal, what's our initial velocity? 75. X is cosine. What's the angle that he hits the ball at? 28 degrees. And that gets multiplied by t. Yes? Okay. Then we've got a y of t function. And that's going to be negative 16 t squared plus 75 times the sine of 28 degrees times t plus 3.5, because that's his initial height. Gravity constant. No. Watch the first part of the video. Okay? Then our second equation that we're going to have in here is we've got the wall. Okay? How far away is the wall? 190 feet. So that's going to be 190 for my x. That's horizontally, it's 190 feet away. How tall is the wall? It's 4 feet. So my y of t is going to be just t, and now I'm going to restrict my t values from 0 to 4. Okay? Here again, old school technology, slow processor technology, this was always cool because you would actually see the ball fly and you would see if the ball crossed the fence. Now it just pops right in because the processors are so much better. Okay? So let's put those into our graphing calculators right now. Let me see if I can do this by doing this. And then, oh, look at that. There we go. Perfect. Oh, nope, I can't. Oh, we'll go up a little bit. There we go. Okay. Now, come on. Why won't it let me do anything now? Okay. So we've got 75 cosines of 28. Oh, I got to go back up to get the degrees. Times t. And then we've got I don't know why it's acting goofy. Okay, so there is mine. We're going to need to definitely change our window. X's, we need to go out to at least 200. Well, it's 190 away, so we got to go out to 200. Ooh, I wouldn't even have to go up to 50. Okay, so here's the flight of Big Al, the ball. Now we've got to put in 190 feet away. We need to put in a wall that is 4 feet tall. Did Big Al hit a home run? He did not hit a home run. He did not live up to his name. Okay? Missed by a lazy pop fly out to center field. Or left field, I should say. Hey, what? I know you did. I was there, remember?
Oh, yeah. Well, I did it twice.
So we'll call you Big Al now.
She, just did it.
Okay? So now the extension question is, do we have enough time? Well, we got plenty of time. Change your 75, increase your 75 to see how fast you would have had to hit it in order to clear the fence. So 87, he hits a home run. And I don't think he hits one at 86. We taught him all about Big Al, Mr. Roth.
Big Al.
Ooh, 86 he does. He does clear that fence at 86. We'll go with 86 then.